We're here today to discuss a critical challenge in medical AI: how to leverage diverse data for better diagnosis while strictly protecting patient privacy. Our work focuses on pneumonia detection, a leading cause of global mortality. We propose a synergistic approach that combines the diagnostic power of multimodal data, X-rays and blood tests, with the privacy-preserving capabilities of federated learning. This integration is essential for moving medical AI from the lab into real-world clinical settings. We believe this framework represents a significant step toward robust, ethical, and deployable diagnostic tools. Let's start by looking at the specific limitations we aim to overcome. Pneumonia remains a major global health concern, and while deep learning offers great promise for diagnostic support, current approaches face two fundamental limitations. First, most models are unimodal. They rely only on chest X-rays. This is unlike a physician who synthesizes information from images, lab results, and patient history for a holistic diagnosis. Second, and perhaps more critically, we face severe data access issues. Strict privacy regulations make it nearly impossible to pool the large, diverse datasets needed to train robust models. Our solution addresses both of these points simultaneously. We combine multimodal learning to integrate X-ray and blood test data, and federated learning to enable collaborative training across hospitals without ever sharing raw patient data. This combined approach, which we call MMFL, is the core of our work. Now, let's briefly review the mechanics of federated learning. To understand how we protect data, we need to clarify the federated learning concept. Federated learning is a distributed machine learning framework designed specifically for decentralized data environments like hospitals. The key principle is simple: the raw data never leaves the local institution. Instead, a central server sends a global model to multiple clients. Each client trains the model locally on their private data. They then send only the updated model parameters, the weights and gradients, back to the server. The server aggregates these updates into an improved global model for the next round. This process ensures patient privacy, enhances data security, and allows us to leverage computational resources across a network of institutions. But before we federate, we first needed to determine the best way to combine our multimodal data streams. Before moving to the decentralized setting, we first experimented with centralized multimodal architectures. To establish a strong performance baseline, we compared two primary fusion strategies for integrating image and tabular data. Intermediate fusion concatenates the feature vectors from the image encoder and the tabular encoder before the final classification layer. Late fusion, on the other hand, trains two independent models, one for the image and one for the tabular data, and combines their probability outputs after training. Our centralized experiments showed a clear winner. The late fusion model, specifically combining a VIT for images and XGBoost for tabular data, achieved the best performance. We saw an accuracy of 95.40% and an AUC of 98.79%. This finding is crucial. It dictates the architecture we must adapt for the federated environment. Let's look at how we translated this high-performing architecture into a privacy-preserving framework. Based on our centralized findings, we propose a multimodal federated learning model using a late fusion strategy. The architecture is decentralized, meaning each client trains two independent models locally: a vision transformer for the X-ray images and an XGBoost model for the blood test results. The challenge here is aggregation, as we have two different model types. For the VIT image model, we use the standard federated averaging, or FedAVG, which averages the network weights across clients. For the XGBoost tabular model, we use a bagging aggregation strategy, which essentially concatenates the decision trees from each client into a single global ensemble. Finally, the outputs of these two global models are combined using late fusion, the Hadamard product, to produce the final pneumonia classification. This dual aggregation strategy allows us to maintain the high performance of the late fusion approach while fully preserving data privacy across the federation. Next, we'll examine the specific dataset and methods we use to test this model. We've just outlined the architecture. Now let's look at the data that powered it. The core of this work relies on a proprietary, anonymized multimodal pneumonia dataset. This dataset is unique because it combines two critical data types: the chest X-ray image and 15 corresponding numerical blood test variables. This multimodal structure is what allows us to mimic a physician's holistic diagnostic process. We worked with 2,343 valid entries from over 2,200 unique patients, ensuring a robust sample size. And here's a key point. We intentionally partition this data into 2 or 3 clients with a non-IID distribution. This setup is crucial because it accurately simulates the messy, heterogeneous data environments we see in real-world hospital federations. Understanding this data structure and its partitioning is essential before we dive into the performance metrics. So let's move on to the results and see how our models performed on this challenging, decentralized data. The results confirm that our multimodal approach provides a powerful diagnostic tool, even in a privacy-preserving setting. Our centralized baseline, the multimodal late fusion model, achieved exceptional performance, 95.40% accuracy and an AUC of nearly 99%. This tells us that combining the image and tabular data is highly effective. Now, the real test was the federated learning model. Operating across 2 simulated clients, the MMFL model achieved 90.33% accuracy and an AUC of 96.67%. This is a strong result. We see about a 5% drop in accuracy compared to the centralized model, but this trade-off is highly acceptable. Why? Because we gain the substantial benefit of data privacy and security. This finding is critical. It proves that federated learning is a viable, high-performing alternative for healthcare settings where data governance is paramount. Let's wrap up by summarizing the impact of this work and discussing where we go next. In summary, we successfully developed and validated a multimodal federated learning framework made for pneumonia detection. This framework is a significant step forward because it addresses the 2 major limitations in medical AI today: the reliance on unimodal data and the challenges of data privacy. We demonstrated that our MMFL approach can effectively integrate X-ray images and blood test data while maintaining patient confidentiality. Achieving over 90% accuracy in a federated setting confirms that collaborative AI development is not only possible, but also highly effective. Looking ahead, we have several exciting avenues for future work. We want to explore intermediate fusion in the federated setting to see if we can squeeze out more performance by integrating features earlier. We also need to test the scalability of this framework with a larger number of clients and more diverse data heterogeneity. Ultimately, our goal is to apply this robust, privacy-preserving MMFL framework to a wider range of medical diagnostic problems. Thank you.